All right, let's think about graphing functions by viewing them as transformations, which are predictable movements in a graph from one of the common functions that we've learned about. So let's think about number one first. Let me open a Cartesian plane, and we're not going to find points. These aren't going to be exact graphs, but what's important here is that you get the idea of what the movements do. What does multiplying a function by a number do if that function is bigger than one, or the number is bigger than one or smaller than one? What does adding or subtracting a number do to the shape, just to get a general idea of what the function is going to look like. So we won't be plotting specific points here, just the rough idea of what each graph is going to do. So there's my y, there's my x. And let's think about number one here. 1/4 x cubed. So let's draw x cubed. Right, as my x values get larger, their cubes also grow at a faster and faster rate. And it's true for the negatives as well, right? But they stay negative, right? If I'm on this side of the y-axis, my x values are negative, and if I cube a negative, it remains negative, right? This is an odd function. So that is my x cubed. Now, what am I doing to x cubed here? So that's x cubed. And now I'm taking all of these x cubed values and dividing them by 4. So I'm making them 1/4 as large as they are. So I'm going to make all of these values 1/4 as small. Maybe let's just do a test point. Let's look at the value 2. So underneath the x cubed function, 2 cubed gives me an 8. So that's 8 right there. But underneath 1/4 x cubed, that gives me 1/4 times 8, or 2. That value right there is a 2, right? I took that 8 value and I cut it into a fourth. I made it 1/4 as large because that's exactly what my function told me to do. It told me to take 1/4 of my x cubed values. So multiplying a function on the outside by a number smaller than 1 is going to shrink all of your y values. It's going to give you a vertical compression, right? I'm compressing my vertical axis, my y values. I'm squeezing those together, and I'm making my original x cubed function flatter. Okay. What about, I should not do dotted lines. They take forever to erase. What about our second function here? The absolute value of x minus 4. So let's again start with the original common function. I'm viewing this as a transformation from the absolute value function. So the absolute value function looks like that v, right? It's equal to x over here. It's equal to minus x over there. All right, and now what am I doing to the absolute value of x? I'm shifting it down by 4 units, right? I'm taking the absolute value of x and I'm subtracting 4. So if this point right here is at 0, 1, 2, 3, 4. Oops, let me change to a different color. So this was the absolute value of x, and this is the absolute value of x, just minus 4 values now. So let's look at another point. Let's look at minus 4 over here. So underneath my original function, the absolute value of 4 returns 4. Underneath my shifted function, the absolute value of 4 minus 4 returns 4 minus 4, or 0. So subtracting a function by a number just shifts it down, right? Same thing if I added 4. If I looked at absolute value of x plus 4, it'd be this function shifted up by 4 units. So adding or subtracting a function by a number just moves you up or down the y-axis. All right, let's think about function number 3. I want to look at 2x. Oops. 2x squared. Oh man, okay, there we go. So I'm going to view this as a transformation of the x squared function. So x squared looks like this, right? 2 squared gives you a 4. So let's label this. This is the original x squared function. Now, if I look at 2x squared, if I multiply the inside of the square function, right, that 2 is being squared. So I'm multiplying x by 2 before I perform the square function. That is going to horizontally compress me by a factor of 2. I'm taking my x-axis because I'm doing something to the inside of the function, and I'm compressing it. Now, if we were to look at the value of 2, that gives me what? 2 times 2 is a 4 times, or 4 squared gives me a 16. So all the way up here, 2 gets mapped up to 16. So multiplying the inside of a function by a number bigger than 1 is going to horizontally compress you. Multiplying the inside of a function by something smaller than 1 is going to horizontally dilate you. All right, function number 4. Function number 4, we're going to view this as a transformation of x to the 4th. So x to the 4th kind of looks like the x squared, except it's a little bit flatter, and it grows much faster as soon as we overtake 1. All right, so x plus 7 to the 4th, what am I doing to this function? I'm adding 7 before I take it to the 4th power. So this is going to be a horizontal change, and it's going to be a horizontal shift to the left by 7 units, right? Because originally, when is x 4th going to give you a 0? That's when x is equal to 0. But now, when is x plus 7 to the 4th going to give you a 0? That's when x plus 7 is equal to 0, or x is equal to minus 7. So instead of having a 0 at 0, you now have it at minus 7. So you shifted to the left by 7 units. But you still have that same shape. So if you add or subtract before you perform the function, like here we added 7 before we took it to the power of 4, then it kind of does the opposite of what you think. If you add 7, then that means it shifts to the left by 7 units. And finally, our last function. I don't know why that's called 2. Should be 5. Y is equal to 2 times the quantity of x minus 1 squared plus 3. So here we have a bunch of different transformations happening, and let's draw them all in sequence. So I'm going to view this initially as my x squared function. So that's x squared. Now, what's being done to x squared? First, I'm shifting it to the right by 1 unit. In fact, let me change colors. So x squared is in yellow. Let's do our next step in red. I'm taking x, I'm subtracting 1 before I square it, so that'll be a shift to the right by 1 unit. So now my 0 doesn't occur at 0, it occurs at 1, but it's the same shape. This is x minus 1 squared. And now let's switch to a different color. What's being done? I'm not adding 3 just yet because I'm adding 3 after I multiply by 2. So that's my next step. I'll now take 2 times the quantity of x minus 1 squared. So I'm multiplying this red function on the outside by 2, thus I'm dilating it vertically by a factor of 2, I'm making that red function twice as big. Right, I took my y-axis and I stretched it vertically. All right, and now let's switch to a different color. Let's go with green for the last step. The last step is to take this blue function, 2 times x minus 1 squared, and then to add 3. So I'm going to take that blue function, and I'm just going to add 3 to all of its values. Adding something on the outside of a function just shifts you that direction. So now I go up 3 units. 1, 2, 3. So by viewing this function, which is kind of complicated, as a sequence of transformations, you can easily tell that it's going to have that sort of shape, right? It's an easy way to get a rough understanding of what the graph of a function is going to look like if you can view it as a sequence of transformations from one of the common functions that we understand well.